Hello, everyone. Our project focus is using adversarial attacks on AI image detection model. And now with a brief introduction of an overview of our project. Starting off, recent advances in machine learning in the past decade have led to the development of groundbreaking AI image generation models. These models can generate a wide variety of images using techniques such as generative adversarial networks or GANs and variational autoencoders. The range of capabilities with what these models can generate is limitless, as they can create new pieces of art, human faces, or new images. The use of AI image generation can help transform many different fields, including fashion, art, technology, and more. However, to the human eye, it may be difficult to spot when an image is created by an AI model. There are some key attributes one can look for in order to tell if an image was created by an AI model, such as blurry text, scrambled text, or weird-looking fingers or appendages on humans, and more. However, human judgment is not always correct. And so one of our goals is to develop and train a model that can accurately tell when an AI or when an image has been AI generated. Additionally, we'll be diving into the process of fooling the model we create using adversarial attacks, which makes it possible for the model to be tricked. An example of this is shown on the slide, where an adversarial attack causes the judgment of an AI model to be clouded and classify things incorrectly.
Now for an overview about the dataset we used. For this project, we used a CIFFAKE dataset, which includes both real and fake images. In addition, this dataset also includes training and testing images, which tailors itself extremely well to developing and implementing our model. With this dataset, we trained our model to be able to separate authentic images from AI-generated images. For some statistics on the CIFFAKE dataset, there are 120,000 RGB images overall, split up into 60,000 real images and 60,000 fake images. Every image is 32 by 32. There are 10 classes, each with 6,000 images. 5,000 of them are used for training and 1,000 are used for testing. This behavior is repeated on the fake images as well, with the images themselves being generated using CompVisSD, an open source LDM. On the right is a visualization of the CIFFAKE dataset complete with real and fake images.
To begin, we considered two different methods to create our model. The first of these methods was a pre-trained model known as a residual network, also known as ResNet. ResNet provided us with the opportunity for fantastic results as it had a deep architecture that avoids using gradients. For this project, we considered ResNet 50. However, in practice, we found that ResNet was too computationally intensive with over 23 million parameters. This was not suitable for our dataset, which only contained 100,000 32 by 32 images.
Then we considered using convolutional neural network, which is CNN. A CNN is a type of neural network that specializes in processing data with a grid-like topology. A CNN is made of three layers. A convolution layer, which performs a dot product between two matrices, where one matrix is the kernel and the other one is the restricted portions of the respective field. A pooling layer, which replaces the output of the network at certain locations by deriving summary statistic of nearby outputs. As you can see in the image, the statistic is maximum. And a fully connected layer, which translates the linear operation convolution to nonlinear as the image. We can see that this means that CNN is faster and gives more control and flexibility over ResNet, and this is why we chose it.
So to create and train our CNN, we use the Google Colab platform. The basic structure of the CNN is shown to the right, the figure 6. This picture depicts the CNN, the structure of the CNN we used. The layers we chose to use, as shown, are an input layer, a resizing layer, a rescaling layer, a convolutional 2D layer, a max pooling layer, a flattened layer, and 2 dense layers. The input layer is the first layer of the CNN that simply helps with the processing of the images. It indicates the expected size of the images that will be inputted, which in this case, a 32 by 32 image with 3 color channels, which is why there's the 32 by 32 by 3. The resizing layer simply resizes the images if need be in order to pass it on to the rescaling layer, which normalizes the pixel value of the images. The convolutional 2D layer is the first actual convolution layer of the model. It takes the now normalized images and applies filters to them. The max pooling layer performs max pooling in order to reduce the dimensions by half. This is done primarily so the computational load is reduced and helps control overfitting. The flattened layer maps the still 2D feature maps into a one-dimensional vector, so the next dense layers will be able to read them, as they only take an input of a one-dimensional vector. The final dense layers are used to apply activation functions to our data, such as ReLU and sigmoid, in order to produce an output between 1 and 0, or true, like real image or fake image, representing the possibility of the input being in one of those classes or the other. After setting up the general structure, we trained and tested our model. The graphs to the right were very helpful when it came to actually visualizing the success of our model. By analyzing the accuracy over epochs graph, we can see that the model is effectively learning from the data. We can also see that the model is generalizing very well to new data as the validation accuracy increases from 82% all the way to 91%. The loss over epochs model shows that the model is getting better at minimizing classification error on the training set, as the loss has increased from 0.1 all the way to 0.0, decreased from 0.4 all the way to 0.05. And finally, the precision over epochs tells us that the model is improving in the proportion of positive identifications that were correct. To conclude with our CNN model, we found it to be very accurate with a rate of about 0.91 and a loss of about 0.22. As we are very happy with these results, we will now try to fool our model by using adversarial attacks.
For an overview on adversarial attacks, adversarial attacks are a critical area of study in machine learning. The purpose of an adversarial attack is to deceive machine learning models and have them make incorrect predictions. They do this by manipulating input data and exploiting weaknesses in neural networks. While these are not visually identifiable to humans, they can drastically alter the interpretations of a machine learning model. As shown in our introduction slide, we chose to use a gradient-based method called fast gradient sign method, hereafter referred to as FGSM. FGSM involves using the gradient of the loss function with respect to input data to create a new image that maximizes that loss. In simplified terms, a small change is made to increase the error in the classifier. To the right is an image showing the equation for FGSM, complete with a legend that shows what each variable in the equation means.
All right, so to implement this in code, we first chose an image that was correctly classified by our model as the input, and from there, we calculated the gradient of the loss function with respect to the input image. So by doing this, we were able to generate the adversarial image by performing computations to determine the magnitude of perturbation. So the adversarial image was created by adding this perturbation to the original image. So as you can see in the code, that's how we implemented it. We take the gradient and the sign of it, and our adversarial example is the original image plus epsilon times the gradient. And so we used an epsilon of 0.01 when generating our adversarial image to make sure that it would fool the model by flipping the classification, but also small enough that it didn't affect how it looked to the human eye. So here are some examples of our implementation. So in the left, you can see the two images that are from the data set, and they have a low predicted probability indicating that they're likely fake, which they were. And then we calculated the gradient that would increase the loss function. And since it's the signed gradient, the pixels are fully saturated. And so we added that to the original image to get our portrayed image, and you can see that the probability is much higher, so 77 and 85%, which means that our adversarial attack succeeded in fooling the model, since it took a fake image and made it look real to the model. And so just to understand why this worked, it's because our model has 462,000 parameters. So it's not modeling the underlying truth, more it's modeling the original data, which our training data is similar to the original data, but when we're adding a gradient, the data is different, and that can lead to an adversarial attack.
And to conclude, our project has shown that CNNs can be used to distinguish between real and AI images with over 90% accuracy. We also implemented an adversarial attack that can be used to fool the detector with manipulations that are not noticeable to humans. This highlights that while CNNs are highly effective at classifying images, they are not impenetrable due to the large number of parameters, and in our case, there's 462,000. It also shows how effective adversarial attacks can be, as we had achieved over 90% accuracy, but an attack can bring that down to less than 10%. This makes them susceptible to target attacks that exploit the gradient of the model's output to trick the classifier into thinking a fake image is real, or vice versa. There are a variety of methods to defend from these types of attacks, such as augmenting the data with noise, implementing regularization, or other methods of altering the loss function to distill the model. Moving forward, we hope to contribute to improvements in model architecture and training methodologies in order to increase the safety and reliability of AI applications. With the rapid improvements in AI image and now video generation, it is very important that security measures are concurrently developed in order to prevent bad faith actors from using AI for harm.